This lesson deals with supplemental problem 8.12. You can find this problem in the ECE202 ebook in the Chapter 8 supplemental problem starting on page 13. Given this parallel resonant circuit, could you find the resonant frequency? This is a model for an AM tuner. And what we're going to do is vary this capacitance until we bring this circuit to resonance and we'll be able to detect a radio station. Suppose that this current source here represents the signal received by an antenna. About 200 picoamps in magnitude, and it's at a frequency of 1.24 megahertz. The radio station I'm trying to locate is called AM1240, which really means 1240 kilohertz or 1.24 megahertz. Suppose that the equivalent circuit of the antenna, besides the current source, is this resistance around 1,000,000 ohms. If I pick an inductance of 360 microhenries, what value of C would I need to bring this to resonance? And then could you find the voltage across the parallel combination and the current through each of these elements in steady state? Well, what does it mean to be in resonance? Well, it means that the equivalent impedance looking into the circuit is purely real. All right, so let's find the input impedance of this circuit. I've got a resistor, an impedance j omega L, and an impedance 1 over j omega C. Now when things are in parallel, it's a little bit easier to add up their admittances and then take the reciprocal of the sum. So let's do that. So my admittance here is 1 over R, 1 over j omega L, and then j omega C. Now you can write 1 over j as minus j. So what I've got then is a minus j, and you're going to plus j. I'm left with minus 1 over omega L, and then omega C. And that's some equivalent conductance and some equivalent susceptance. Resonance, this is going to be purely real, which means that the reciprocal is purely real, and that implies that the susceptance must be equal to 0. So let's just say that occurs at one frequency called omega naught. And so setting that susceptance equal to 0, we then have minus omega naught L plus omega naught C. Put this on the other side of the equation as a positive. We can cross multiply here. So we get omega naught squared is equal to 1 over LC. And so omega naught is 1 over the square root of LC. Divide by 2 pi and you get the value of the resonant frequency in hertz. Now we know the frequency of our radio station. We know the value of L. We solve for the value of C. It turns out to be 1 over 2 pi, 1240 kilohertz, quantity squared, times 360 microhenries. It would be 45.76 picofarads. So we're going to vary this capacitance until we get a value of 45.76 picofarads. And that's going to be something we could measure, but actually it's easier just to tune this and then listen to the radio. So when you find the radio station, it'll come in louder at that particular value of capacitance. The way this is actually made is with sets of metal plates interleaved. As you rotate it, you're changing the area between the plates, and that's changing the effective capacitance. And you get variations into the dozens of picofarads. Let's find the voltages and the currents that we were asked to. Let's use our three-step algorithm to find the results. So our current source is 200 picoamps with a cosine with an angle of 0. The frequency is 2 pi times 1240 kilohertz, and that's 7.791 megaradians per second. The resistor is still a resistor, but our inductor is j omega L, so with the 360 microhenries that we had, gives me a value of j 2.81 k ohms. With the value of capacitance we solved on the previous page, the minus j over omega C is equal to minus j 2.81 k. Parallel combination of these three we can form, but let's take the two reactive terms together here. So I'll take the product over the sum, but if you notice the denominator here, we've got two equal and opposite terms, so that's going to be equal to 0. And 1 over 0 is infinity, provided that the numerator is finite. So the parallel combination is just that of the resistance of 1 megohm. The voltage across the parallel combination would just be this current flowing into this parallel combination. 1 megohm at angle 0 and 200 picoamps at angle 0 gives me 200 microvolts at angle 0. Again, this is typical of what you would see coming off an antenna. Pretty tiny signal. Current then in this resistance is going to be the voltage across the parallel combination divided by the resistance, and that turns out to be 200 picoamps at angle 0. What that's implying is that all this current is going into here. There's nothing left over here and nothing coming back. But there's a voltage across this parallel combination, so we could calculate the current in this direction. It's going to be the 200 microvolts at angle 0 divided by j 2.1 k, which is 2.81 k at angle 90. That gives me a value of 71.17 nanoamps at angle minus 90. There is a current flowing in here. That current can't go this way, it has to go this way. Let's calculate the current in this direction though. 200 microvolts at angle 0 divided by minus j 2.81 k. And that's equal to 2.81 k at angle minus 90. Then my overall ratio is the same as last time, but the angle now is 0 minus 90. So these two are 180 degrees apart. In other words, they're in opposite directions. What we really have is a current going in this direction. So what's happening now is all of this current is flowing in here, but there is a current circulating between the L and C. What can that be? Well, during the transient analysis, we're going from our initial values to eventually these steady state values, and some of the energy then is built up in the L and C, and it's just swapping it back and forth. And lastly, to find the time domain steady state results, just put the cosine of omega t between the magnitude and the angle. So we got 200 microvolts, cosine of 2 pi, 0.2 megahertz, T. The current is 200 picoamps, cosine of the same frequency. The current in the inductor is 71.17 times the cosine, same frequency, with minus 90 degrees, and then the capacitor plus 90 degrees. Now what's happening at resonance is that we're getting the L and C canceling each other, and we're actually getting just the resistance left over. To explain this, let me go back up to the circuit. And when we're at resonance, these two cancel, and all I see is this 1 megohm resistance. Now when we go off of resonance, we go lower and lower in frequency, this inductor becomes a short circuit, and this capacitor becomes an open circuit. So the impedance goes down. When you go above resonance, the opposite happens. The capacitor gets smaller and smaller impedance as the frequency goes up, looks more like a short circuit. And the inductor looks more like an open circuit. So at resonance, we have actually the largest value of impedance that we're going to have. The lower and higher will be going down in value. So we have the maximum resistance at resonance. If you have a weak signal coming in, think of it as a current, all that current is going to flow in here and produce the largest voltage. And we're going to use that then to sense the radio station and then to do some demodulation and then play eventually the signal that was received. Why don't you do some of this in ECE404? And this is supplemental problem 812.